And we can easily calculate the magnetic susceptibility, magnetic permeability, and we can also determine that whether the some axis is easy axis or a hard axis. And in the right hand side, you can see this is the hysteresis loop. This is actually measure magnetic flux density as a function of magnetic field. If we get this hysteresis loop, then we can easily determine what is the retentivity or perceptibility. So to measure these properties of magnetic material, there is lots of technique in market. So I will talk about two basic technique. That is the first two technique, that is vibrating sample magnetometer VSM and DC SQUID magnetometer. I will talk about these two. So let's start for this vibrating sample magnetometer. This vibrating sample magnetometer was first invented or successfully reported by Simon Foner in 1959 in the Journal of Review of Scientific Instruments. And you can see in the right hand side, this is the typical vibrating sample magnetometer VSM. So let's go to that schematic diagram. Before to go to schematic diagram, from the name vibrating sample magnetometer, you can easily understand that vibrating sample, that means sample will vibrate here. Let me take the laser point here. So this number 5, this is our sample, and it will vibrate along the z-axis. So this is actually vibrating sample, and this is whole system is called magnetometer. That is why it is called as vibrating sample magnetometer. And this sample will vibrate using some speaker. This is the speaker setup, and using this speaker, this will vibrate along the z-axis. And here will be obviously some measuring instrument will be there to measure what intensity it is vibrating over here. I am not going into those details, but somehow it will vibrate, and we can measure the intensity of vibration. So whatever. And this is a drinking straw strip. Drinking straw. We put the sample over here, and this sample will come over here. And this number 8, this is magnetic pole pieces, and it will generate magnetic field, and magnetic field will cross over the magnetic sample, and it will experience some magnetic field. And whenever this will vibrate along the z-axis, it will make some magnetic flux change over here. And due to this magnetic flux change, these two pickup coils over here, the number 7, these two pickup coils will experience some induced EMF. As we know that induced EMF is proportional to the change in magnetic flux. So this will experience the magnetic EMF, induced EMF. And if we measure this magnetic induced EMF, then we can easily understand that what is the value of magnetization. And there are lots of calculations and one computation analysis to make some relation between the EMF and the magnetization. So, and in the right hand side, this is the zoomed in picture of this vibrating sample magnetometer. This number 5 are the magnetic pole pieces, and this one is are the pickup coils, and 2 is the sample, and this is the straw strip. So this is the basic understanding of vibrating sample magnetometer. So how to measure the magnetization? As I said, that change in position of the magnetic sample along the z-axis, it will vibrate along the z-axis, and it will associate some induced EMF to the pickup coils, which is related to the change in magnetic flux. And if we measure this EMF using some proper calibration and quantitative analysis, we will get the value of magnetization. I am not going into those details. What is the quantitative analysis is done, but we get some information about the magnetization. So this kind of hysteresis loop we can get from the vibrating sample magnetometer. This is, we can measure the retentivity, coercitivity from this curve also. So this is the basic working principle of vibrating sample magnetometer. So now I am going to the DC SQUID magnetometer. So what is actually SQUID? SQUID is the abbreviation for superconducting quantum interference device. So let me talk about some brief history about this SQUID. In 1962, Josephson actually theoretically proposed that there should be some Josephson tunneling. And in 1963, John Ravel and Philip Anderson successfully made this Josephson junction. And in the next year, 1964, this is SQUID invented by the Robert Jacklib. So this is the basic brief history. And before I go to the working principle, this is better to know that why we should use this SQUID. So actually, this SQUID is the so sensitive. No other instrument can measure this such low magnetic field, and this SQUID can measure such low magnetic field as 5 into 10 to the power minus 14 Tesla. And it is interesting to know that the Earth magnetic field through a red blood cell of a human being, it is about 5 into 10 to the power minus 4 Tesla. So you can understand that how low magnetic field it can measure by this SQUID. And due to this property, we can use this SQUID as a geomagnetic field measurement also. And SQUID is very less noisy also. So these are those advantages. So to understand this SQUID phenomena, we need to have some knowledge about superconducting, superconductivity, and some knowledge about DC Josephson tunneling, and some knowledge about phases of electron pairs, that is flux quantization. So I would like to discuss that. If you look at that this green shape, it is phase matched. That is, if I go round over here, this will be this phase must be some integer value of 2 pi, and here is phase mismatching if we look into the red one. So these three concepts we need to understand the SQUID. So first of all, what is superconductor? Superconductor is some metal which actually shows superconducting behavior below some temperature. This is called transition temperature, and above it shows normal metal. So to explain this superconducting behavior, three scientists they gave BCS theory in 1972, and they gave an idea about Cooper pair. So how Cooper pairs is work? Actually, in low temperature, when thermal fluctuation is become very low, one electron if travel through some positive ions, then this electron will attract towards it some positive ions, and here some area of higher positive charge will occur. And if some electron will placed over here, then this electron will feel attraction towards the area of higher positive charge, and then this electron will come over here, and the two electron will make some pair. So this is called actually Cooper pairs, and this is how superconducting phenomena we can explain. So now next is the DC Josephson tunneling. So Josephson actually given an idea about that Josephson tunneling. If we place an insulator between two superconductors, then Cooper pair will travel from one superconductor to other superconductor using some quantum tunneling, and there must be some representation of wave function, as you can see over here. For first superconductor, if wave function is like this, and second wave function is like this, and in between them there will be some phase differences over there. This is actually phase of the electrons. So if there is no current flow, then there in between two distance x and y, there will be no phase change. That is, phase will be the constant. But in case of if current is flowing, then the phase change between the x and y, it will be proportional to the current. That is actually current density, or this is proportional to the current density. And this superconducting current is actually sinusoidally connected to the phase changes and with the characterized by the critical current. And this critical current is actually depends on the size of the junction, what we chosen, and superconducting material also, and operating temperature. So this concept is very important to understand the SQUID. And if there is interesting phenomena, if there is magnetic field, we apply magnetic field, then the momentum will change, and there will be a role of some magnetic vector potential will come, and this phase change from x and y, it will contributed from two parts, that is phase changes due to current and phase changes due to change of flux density. So now the interesting phenomena, if this superconductor is not linear, if this is in round shape or circular shape, then the first point and the last point, that is x and y, will be the same point. And to realize this, point of phase change will be the some integer value, that is n into 2 pi. So integer value of 2 pi, and this del phi is actually n into phi naught. So this is actually called as first quantum, and this will be some integer value. Okay, and so this concept actually we will use over here, and this is a basic schematic diagram of the DC squid. Actually, this gray shape, you can see this is superconductor for both sides, and we placed parallelly two insulator over here. So this is Josephson junction, and this is also a Josephson junction. In DC squid, we actually use two Josephson junction, and in there is also another squid that is called RF Josephson, radio frequency squid. There we actually use one Josephson junction over there, and we will apply some biasing current over here. One current will go over here, it will break in two parts, and it will again meet over here. And we also apply some magnetic field over here, magnetic flux over here, you can see. So as I said, two basic concepts, that is the change of phase due to magnetic field and change of phase due to two junction, that is a two factor over here. It will be must be quantized. And we also have some knowledge about superconducting current, that is I is equals to IC into sine del phi. So this is the some diagram. This is easy to understand. If this IC and IC, it is critical current over this Josephson junction, and if we apply the current over here, it will break down in I by 2 and I by 2 over here. It will go over here, it will go over here. And if we apply some magnetic flux over here, it will generate some current over here, and this current will go in unit direction. And since this current will go in both directions, then here will be the cancellation of charge, cancellation of current, and here will be the cancellation of addition of current. So this the lower portion, in the lower portion junction, the critical current will achieve earlier than this. So this concept actually we are using over. If I represent this graphical representation, then the circulating current will increase proportion to the magnetic flux until the point correspond to the half of the quantum. Whenever the half quantum, it will be the maximum. And since the circulating current proportional to the energy at the peak point, it is energetically favorable to reverse direction to maintain the same magnitude. So it will reverse over here, and again it will restoring the original state in the integer quantum number. Okay, and this is for this magnetic flux, and this for critical current, this will be 2I0. Since this critical, if there is no current, this current will add over here, and this will be maximum 2I0. So if for this curve, since there is a phase mismatch between the two Josephson terminals, there will be phase mismatch, and due to this, when there is a positive circulating current in the lower side of this squid, then this will fluctuate over. This will decrease to the half quantum number, and this will again increase to the integer quantum number, and this will show as some oscillating function over here. So using this concept and you getting this data from this DC squid, this current is related to this phase, or also related to, and current is also related to the same phase changes, and this phase is related to the magnetic field, magnetic flux. So using this there is some difficult quantitative analysis, and with this quantitative analysis and some easy calculation, we can get some data about this magnetization. So this is how we can get some data about magnetization over temperature as a function of temperature, as a function of heat. So this is basic function of this SQUID, and its application, as I can say, it is it can be used in medical imaging, as it can read human brain waves, but it is in a theoretical phase. It's not applicable in right now, and we can use it also for measures geological magnet, and also to measure astrophysics, magnetic field from astro waves. So these are some references we shall